Hi, this tutorial covers the shape of a sampling distribution. So let's suppose that a population of some random variable x, such as the height of all adult females, the number of siblings in a U.S. high school, or siblings of U.S. high school students, etc., is distributed with a mean of mu sub x and a standard deviation of sigma sub x. Okay, a lot of times you'll see these mean and standard deviation without the subscripts, so you'll just see them as mu and sigma. Since we defined our variable x here, this just means the average x standard deviation of x. So and these are both population parameters because we're dealing with a population here, not just a sample. Okay, so now suppose we took samples of size n from this population and calculated a sample mean x bar from each sample. Okay, so let's say we took a sample of 50 adult females. We could then calculate the average height of those 50 females, and we'd represent that using x bar. Now, if we did that multiple times, the collection of those sample means of our various samples is called the sampling distribution of sample means. All right, so like any distribution, it's helpful to know about the center, the variation, and the shape of the sampling distributions of sample means. Okay, so today we're just going to concentrate on shape. Okay, a theorem that helps us determine the shape of those sampling distributions is called the central limit theorem. And it is a theorem that states that the shape of a sampling distribution of sample means will be approximately normal under certain conditions. Okay, approximately normal is really, really important because we know a lot of things about normal distributions. We know how to calculate percentages by applying z-scores. So it's going to be good to have a normal sampling distribution. Okay, but like I said, there are some certain conditions. So the conditions for the central limit theorem, condition 1 is that the size of the repeated samples must be greater than or equal to 30. Okay, so n has to be greater than or equal to 30. Okay, and 2, the population mean and standard deviation must be finite. Okay, so they can't you can't have like an infinite range of possible values. So the population mean and standard deviation must be finite. Okay, so let's just take a look at a population distribution, and let's think about what that sampling distribution might look like. Okay, so if this were my population, this pretty large population, we're measuring the scores of something. They ranged from 2 to 30. Now, if we were to make a sampling distribution of x bar, our sample means would also have to be between 2 and 30. Okay, so if we were to set up our sampling distribution, again, if you were to take a certain means, they would have to fall in that same range. Okay, so the reason why your population, well, let's start with that first condition. So you have to take samples of size greater than or equal to 30. Okay, so what this sampling distribution is going to look like is it's going to be some sort of approximately normal distribution. That's going to look something like that, where this bulge here should be similar to where your mean is going to be. So our mean will be somewhere in this range. These values will pull it down a little bit, but it should be normal. Okay, but remember, n has to be greater than or equal to 30. The reason why is that in order for this to take that normal distribution, when you sample your 30 values, if it's 30 or greater, if you end up with some of these really low values in your sample, so if you end up with a 2 or a 3 or a 4, it's not going to have a major effect on your sample mean if n is sufficiently large. So if n is greater than 30, these if you happen to get a small value, it's not going to really throw off your mean. So chances of you getting an x bar value over here are going to be very low. Okay, if you're taking again a sample of greater than or equal to 30, chances are you're going to get a sample mean in this range here. So that's kind of the reason behind having a sample greater than or equal to 30. Now your mean and standard deviation of your population must be finite. Okay, the reason for that is that obviously if you have an infinite x-axis and any value were possible, there'd really be no way to figure out where this thing's going to be centered at, and you certainly then would not be able to get that normal distribution, because if you ended up, let's say that there was a value over here at 400, way off of this range. If you sample that value, that's really going to throw off your mean, and if you get that a couple times, you might not get that normal shape. Okay, same with standard deviation. Your standard deviation must also be finite. You can't have an infinite range of values or an infinite standard deviation, because again, those values really far from the mean might throw off this shape. Okay, so again, the central limit theorem states that your sampling distribution of sample means will be approximately normal as long as n is greater than or equal to 30 and that your population mean and standard deviation are finite. So that has been the tutorial on the shape of a sampling distribution. Thanks for watching.